Hi everybody, it's Mr. Molikash again. Welcome back to another Calculus 1 topic, actually 3 topics. This video is going to talk about the first derivative test, which is really a test for finding relative maxes and mins, or what we call relative extrema. We'll talk about concavity, and then we'll talk about the second derivative test and what that means in relationship to the first derivative test. So we've got a couple of examples here, but I'm going to quote from my book here. Again, if you want a copy of this book that I'm using in these videos, just shoot me an email or send me a comment. Like and subscribe, as everybody says. But I do want you to really just watch this. I'm going to work out everything that I'm going to talk about in this book on the white screen, and but everything is worked out in great detail, so if you're a reader and you want to read through this, then I'd be happy to give you a copy of the book. It's a PDF document. Doesn't take up very much space. So the first thing is like relative extrema. So in the previous video I talked about absolute extrema on a closed interval, and I talked about relative extrema, which are highest points relative to the small neighborhood around it, right? And lowest points relative to the small neighborhood around it. And those extreme values in their own neighborhood, if you will, are different than finding absolute extrema on a closed interval, which is what we talked about in my last video. So what we really need to talk about there is why the first derivative of a function helps us find those points, and it's because of this, and I'll show you this in a moment. We'll come back to this, but a function f of x has a relative maximum at a value at x equals a if and only if f of a exists. So you have to have a point there, and the graph of f changes from increasing to decreasing. Equivalently, f has a relative maximum at x equals a if and only if f prime, the derivative, changes from positive to negative. So we're going to use the fact that in any function, and this is not necessarily these examples up here, but in any function, let's say you have x values and you have these critical numbers, right? So maybe you have x equals a and x equals b, and you have something that's going on with the function values, but then you also are keeping track of what's going on with the derivative values, right? So what we say is if the derivative of a function is, first of all, these wouldn't be critical numbers unless the derivative was 0 or undefined, right? So maybe this is undefined, right? And maybe f of x is, I don't know, here it's, we'll say f of a, and then we'll say f of b. So there are y values, but maybe at b f of b there's a sharp point or something, right? So what we're saying is if the derivative is positive, the function has a positive slope, which means it is increasing. Okay, this is my little arrow to say that the function is increasing. That's what we're talking about right here, right? If a function's derivative values are negative between two critical numbers, then we say the function is decreasing between those two critical numbers. And if this kind of thing happens, if the sign changes from positive to negative for the derivative, then look what's happening to the function. We go from increasing to decreasing, and we say that f of a is a relative maximum. Okay, relative. It may not be the very highest point on the graph, but that kind of thing. And if the value of the derivative changes again to a positive number, then it's increasing. So maybe and this would be in this case relative minimum, right? Okay, so if we were drawing this graph, right, we may have a here and b here, and here's f of a, and maybe down here is f of b. So what could be happening, right, is up to x equals a, the function is increasing, and then it decreases, right? And then we have a point, sorry, went a little bit too far down. Let's try that again. I want to get to that point right there, f of b, and then, maybe it's increasing again. So, we have a sharp point here, so the derivative's undefined, but we still have a relative minimum, right? So this is a relative minimum value, and this is a relative maximum value. And it's not the absolute, right? Because there's definitely smaller values here, and there may be bigger values here, but relative to the neighborhood around that point. This is the highest point in the neighborhood, this is the lowest point in the neighborhood. Okay, so that's kind of what's going on. Whoa, I did not mean to do that. Okay. Alright, so let's go through a couple of examples here. I'm not sure what's going on with my pen software, but we're going to look at how to find the relative extrema, the relative maxes and mins for our function f of x here. And as soon as I can erase the board. And we're going to do this without ever using a graphing calculator. So if you're one of my students, you know that when you take tests in my class that you cannot use a graphing calculator. That's a requirement for Calculus 1 at JCC and also NC State, right? Now occasionally you get to use Maple for certain assignments and that kind of thing, but what we want is we want you to be able to find these points without the aid of a graphing calculator. That's required for you in this course algebraically, right? So we're going to do this algebraically. Okay. Alright, now that I've done erasing everything, let's take a look at our first example. So let's say that we have our function that I have listed up here. This is a cubic, 2x cubed minus 3x squared plus 2. So the first thing I'm going to do is try to find my critical number. So I'm going to take the derivative of this function, which at this point for you should be pretty easy, I would imagine. Okay. And the derivative is defined for all x, so there's no critical numbers where the derivative is undefined. But we're going to say a critical numbers happen where the derivative is equal to 0. Now, we also have to consider where the derivative is undefined, and that's why we have a second example here. But let's go ahead and solve this real quick. So we can solve this by factoring, and we get x equals 0 from this factor, and we get x equals 1. Good. So we've got a couple of critical numbers that we can put on the number line, right? I'm not sure why that's not working out. Oh, wow. Well, what I want to put down there is x equals 0. I must have had the eraser tool going on by accident here. Not quite sure what's going on. Alright. Maybe if I come down here. Tell you what I do. I'm going to get rid of my Epic Pen software because it doesn't seem to be wanting to cooperate with me. I'm telling it to do too many things, I think. Okay, so I've got a couple of examples here and noted on this textbook, so let's try this again. So again, f of x was 2x cubed minus 3x squared plus 2. We took our derivative. We found our critical numbers. And that's where our derivative in this case is equal to 0. And we found out that those were x equals 0 and x equals 1. Those are solutions to this equation down here. So what we'd like to do, now we're working good, is put these critical numbers on a number line, okay? And we're going to keep track of two things. We're going to keep track of the derivative values at intervals before and after these, and we're going to make a conclusion about function behavior, okay? Alright, so what we know here is that at this value, the derivative equals 0. Our derivative equals 0 when we plug those numbers in. Right, so we get 0 for the derivative. Alright, so all that means right now is that our function has a horizontal tangent line. We don't know what happens before and after it yet, until, this is where the test comes in. We get to pick a number in each interval. So I get to pick a number like, let's say, -1. I'm going to plug that into my derivative and see if I get a positive or negative. So I can do that here real easily. If I put x equals -1 here, at x equals -1, when f prime of -1 would be -6 times -2, right? And that's positive 12. I'm not so concerned about the 12, I'm really concerned about the positive. Okay, since the derivative is positive, we can conclude that our function is increasing. Okay, now you may have to rewind the video and watch that again. I'm going to pick another number in between 0 and 1 and do the same thing. So let's say 1/2, that would work, right? So if x equals 1/2, I want to find the sign of the derivative value, right? So f prime of 1/2, if I put 1/2 here, I get 6 times 1/2, which is 3, and 1/2 minus 1 is -1/2, and this is negative, right? So at x equals 1/2, the function has a negative derivative, which means that at x equals 0, f of 0 is a relative maximum. So let me put that up here. We now know that f of 0 is a relative maximum. Now to find f of 0, I'm going to use the function, not the derivative, right? That's why it's really important when you're doing this to label everything. It's a lot of information to keep up with. Okay. Alright, let's pick another number over here. Let's say like x equals 2. We can do this real quickly. So what's f prime of 2? That's 6 times 2, which is 12. And then 2 minus 1 is 1. This is definitely a positive number, and the function is increasing on the interval from 1 to infinity. So we can say that f of 1 is a relative minimum. Okay, so what do we do for f of 0, right? What is f of 0? F of 0 comes in here. And you can see real quickly, if I put 0 in there, I'm just going to get 2. So the function's value at 0 is 2, and that is a relative maximum. And at 1, I get to put 1 in here, so if I do 1 any power, I get 1. So that's 2 minus 3 plus 2, which is 1. And that's a relative minimum. Okay, so this is the answer to finding the relative minimum, and it uses the first derivative test. Okay, now you can kind of see up here a sort of graph, right? Like the way that a cubic function would look. This is telling you what the graph of f looks like. It starts increasing, it comes back down, and it comes back up again. So the function looks like this. It has a relative maximum and a relative minimum, and sure enough, this is what a cubic function looks like, right? Okay, but now we know that this y value here is 2, and it happens at 0, and then this 0.11 is a relative minimum. Okay, so we're going to talk about concavity now, and then I'm going to use another example. Okay, concavity. So concavity has to do with the second derivative. And so if I go and put the second derivative values and if I do this entire thing but change my f prime to f double prime, it will tell me where the change in concavity is. So you might be asking, like, what the heck is concavity? Well, you might have to go back to my last video where I talked about that. Concavity is determined by the second derivative and is a measure of how much the curve deviates from being linear. So if a graph is curved upwards, like y equals x squared, it's said to be concave up, right? So we talked about that some again in the last video, but concave up graphs, instead of being, this is an increasing function, but this is a concave up function, right? So this looks like a line, and this looks like a parabola, right? So that's why I kind of referenced this example, because that graph is on its entire domain is concave up. Concave down looks like this. Okay, all right. So what we're going to do is this problem all over again. Okay, but we're going to get different, I'm going to say, candidates for these points where concavity changes, and those are called inflection points. If you read on here, we learn how to points on the graph of a function where concavity changes. So this is where it curves up and then it curves down and that kind of thing. Okay, all right. So let's say we have our same function, 2x cubed minus 3x squared plus 2. And we go and find our second derivative. So our first derivative, if you remember earlier in the video, was this. But I'm going to keep going and find the second order derivative. So that's going to give me 12x minus 6. Now, where the second derivative is equal to 0, you have a possibility, and I mean possibility, okay? A function has an inflection point if and only if f of a exists and the graph of f changes concavity. Equivalently, f has an inflection point at x equals a if and only if f prime changes sign, f double prime rather changes sign at x equals a. So let's see how that point that I made just kind of plays out here. So we're going to say that we have possible inflection points happen where f double prime is equal to 0. And so we have an expression for f double prime, and we're going to set that equal to 0, and we can do the math pretty easily. You get 1/2. So what are we going to do with 1/2? Well, on our number line, we're going to put 1/2. Now, I'm not calling this a critical number. I'm calling this a possible inflection point. Critical numbers are where the first derivative equals 0 or is undefined. So 1/2 is not a critical number. Don't make that mistake. So what am I going to do? I'm going to do the same math that I did before, but I'm going to plug numbers into f double prime and make some conclusions about the graph of f. So we could have used some pretty easy numbers like 0 and 1, right? By the way, the second derivative value is 0 at this point. So what does that mean? Absolutely nothing. The second derivative being 0 means absolutely nothing. It just means that around that area, the graph looks like a line. It's not curved up or curved down. It has 0 concavity in that particular space. Okay. Other than that, it doesn't mean really anything much. But let's put 0 into this expression. If we do that, we get -6. So what does that mean about the graph of f? Well, remember, if the graph of f is concave down, it has a negative second derivative. So this means that the graph is concave down at that point. Okay. If we put positive 1 in here, we get 12 minus 6, which is positive, and the graph is concave up. Okay. So what does this mean? This means that at f of 1/2, 1/2 comma f of 1/2 is an inflection point. And I can say that because f is defined at 1/2, right? Alright, so basically what's going on is we have a point here, 1, 1. We have a point here, 0, 2. And somewhere in here at 1/2 and whatever the y value is at 1/2, okay, the graph changed from being curved downward like this, concave down, to being curved upward like this, concave up. Okay, so this is called an inflection point. The inflection point. And that is where the concavity of the graph changes. Okay? Alright, now our final thing to do with this function is to do what's called the second derivative test. And what we're going to do is we're going to go back and look at these critical numbers again. Okay? So let me adjust this, let me adjust my number line and go back to an earlier part of the video. Okay? Let me go back to an earlier part of the video where we just had f prime when we were doing the first derivative test. Okay? So what the second derivative test does is it allows you to find maximums and minimums without having to test values before and after your critical numbers. Okay, so let's see if I can make all this go away. My erasing tool is not erasing very easily. I wish I had a better eraser, but I have a Mac and I don't have all that great of a drawing software. Alright, and I can leave all that up there. Alright, so just kind of remember that earlier in the video, remember we had critical numbers where this was equal to 0, right? And that will happen at x equals 0 and x equals 1. You can rewind the video a little bit to see why that happened. Okay, and remember the first derivative here was 0 and 0. The first derivative was positive. Our function was increasing, right? And all that. But let's kind of take this out, and instead of having to talk about what happens before and after the critical numbers, okay, what we're going to do is we're going to put these numbers, the critical numbers, into the second derivative. Not this number, the critical numbers are now going to go into the second derivative. Now, stay with me and watch this. You'll see why I'm doing that. So if I put 0 into this, I get a negative, right? If I put 1 into this, I get a positive. Now, what does that mean? It means at x equals 0, the function is concave down, but at 0, there is also a horizontal tangent line, right? So it's not just curved down, but at this point we can say there is a relative maximum at 0 f of 0. Specifically because we know not only is the derivative equal to 0, but at that place it's also concave down. So if it's concave down and has a horizontal tangent, then we can use this second derivative test to conclude that we have a relative maximum there, and that means we don't care about what happens before and after it. We can just straight up use our critical numbers. Now the catch for this is that you have to use this in both derivatives, right? So again, if you put 1 into your second derivative, you get 12 minus 6, which is positive. Remember, our first derivative was 0, but the function is concave up, right? So we have this going on. We have a horizontal tangent line at a place where the function is concave up, so that means we have a relative minimum at 1 f of 1. Okay? And again, to find f of anything, you have to use the original equation that they gave you for the function, not the first or second derivative. Okay? Yeah, there's a lot of information to keep up with here, so I would encourage you to go back and take notes, slow things down, work through the example on your own, and then come to me with questions if you need to. Okay, let's take a look at this other example, and I'll quickly go through this because I don't want to make this video too long, but I do think this is an important example because on this particular function there's something that happens that didn't happen on the first one. Okay, so let's do our first derivative test. So let's find our first derivative, which is 2/3 times 3, that's going to be 2, and then we have to reduce this by 1 and get negative 1/3. By the way, if you're one of my students, you should know how to find these derivatives pretty quickly. You should know how to find the derivatives of trig functions, exponential functions, logarithm is coming, right? Alright, let's multiply that by 3, and then the derivative of a constant is 0. Okay, great. Now, we have a negative exponent. So what does that mean? That means that this is 2 over x to the 1/3 minus 2x squared. Now, right now, you can see that g prime of 0 is undefined. Why is that? Because if I put 0 in the place of x, I'm dividing by 0, right? Now, the function is defined at 0, right? If I could put 0 in here and be just fine. In fact, I can real quickly I can just put 0 in and say g of 0 is negative 1, but the derivative is undefined. So that tells me that around that point 0 negative 1, that there's some kind of sharp point going on, right, or something like that. Okay, so right now this means that 0 is a critical number. So therefore x equals 0 is a critical number. Alright, now how do I find the other critical numbers if they exist? Well, the other ones happen to be where this stuff is equal to 0, right? Okay, now I can multiply everything through by, I guess, x to the 1/3 to find out where it's equal to 0, right? Because I've already considered the fact that x is not 0. That's another critical number, right? So if I multiply everything by x to the 1/3, then I get 2 minus, what's x squared? Let's see, x squared times x to the 1/3. That's x to the 6/3 times x to the 1/3. That's x to the 7/3. Okay, so this is 2x to the 7/3. And then I can divide everything by 2. Add this to the other side. Okay, so then what have I got to do? Then I've got to raise everything to the 3/7 to make my exponent of x equal to 1, right? So x equals 1 is another critical number, right? So g prime of 1 is 0, therefore x equals 1 is a critical number. So we have two different kinds of critical numbers in this problem. We have one where the derivative is undefined. We have one where the derivative is 0. On the previous problem, both critical numbers gave us 0 for the derivative. The derivative was defined everywhere, right? Okay. So what are we going to do with our critical numbers, right? Well, what we have to do with our critical numbers is put them on a number line, all that kind of stuff, and I'm not having much luck with erasing. So what I'm going to do is just kind of continue on over here with my number line. So when x is 0, and I guess I should say g prime of x is undefined. When x is 1, g prime of 1 is 0. Okay, so we could do this first derivative test, right? So we could put in a number like, I don't know, -1 into our derivative. Now if we do that, we have to do the cube root of -1, which is -1. So that would be -2. And then we square -1, we get 1. So that would be 2 minus, wait a minute, that would be -2 minus 2, which is -4. When you think about that, right? 2 divided by the cube root of -1, that's 2 divided by -1, which is -1. And then 2 divided by -1 is -2, minus 2 times 1. Okay, so that's negative, so our function is decreasing. If we put something like 1/2 in there, oh, what's the cube root of 1/2? I think that's 1/8. And 2 divided by 1/8 would be 16. And 16 minus 2 times 1/4, that's definitely positive. Okay, and then let's put a big number like 2 in there. So then we have, let's put a better number like 8. 8 is a better number, right? Easier number to take a cube root of. So the cube root of 8 is 2. 2 divided by 2 is 1. If we put 8 there, it's 1 minus that is going to definitely be negative. So this is what our graph looks like, right? So we can say that 0, f of 0 is a relative what? Relative minimum, because the derivative changed from negative to positive, and the function, which I forgot to label up here, is changing from decreasing to increasing. And then 1 f of 1 is a relative maximum. Now to figure out what f of 0 is, you just put that up here, right? So I suppose what we could do is just put 0 in place of x. So what is 0 evaluated into g of x? That's just going to give us -1, right? And then if we put 1 in there, we get 3 minus 2/3 minus 1. So 2, it's like, let's see, 3 minus 1 is 2. 2 minus 2/3 is 4/3. So at 1 comma 4/3, on this graph of this function, you're going to have a relative maximum. Okay. Now, could we do the second derivative test on this? Maybe. I'm guessing that we really can't, because if the first derivative is undefined at 0, chances are the second derivative is also going to be undefined at 0, and you're not going to be able to put 0 into your second derivative, right? So the second derivative test is only really going to work if you have a derivative that's defined at your critical numbers. Okay? Alright, so in conclusion, let's go conclude some things. A function has a relative minimum at x equals a if and only if f of a exists. The graph of f changes from increasing to decreasing at x equals a. Equivalently, that means that the function's derivative changes from positive to negative, right? Minimum values, relative minimum happens where the derivative changes from negative to positive, and that means that the function is changing from decreasing to increasing. Also, an inflection point happens where the second derivative changes sign, right? The second derivative has to change sign. It's not enough to say that the second derivative is 0. It has to change sign. You have to do your pluses and minuses, okay? And then finally, couple of conclusions to make. Relative extreme and inflection points for a function must occur at values where f is continuous. In other words, the function has to have a point there. There has to be a f of a, right? Relative extreme and inflection points for a function may occur at the values where f is not differentiable, like that sharp point, right? And then thirdly, relative extreme and inflection points for a function may or may not occur at values where f prime is equal to 0, or where f prime is undefined. F double prime in the case of inflection points. The value of the derivative is not enough. We must show a sign change. That's the reason why you have to do your plus and your minus to get your increasing and decreasing. So just knowing that the derivative itself is 0 is not enough information, okay? And then the second derivative test, you want to do, as in the first derivative test, you find your critical numbers, but you put them into the second derivative, right? You put those critical numbers into the second derivative and find the sign, right? And then you conclude that the function has a maximum or minimum where the second derivative is negative, that would be a maximum, or if the second derivative is positive, that would be concave up and would be a minimum. Okay, so there's a couple of pictures that go along with the second derivative test. And in most cases, the second derivative test is optional. You do not have to use it, but it can be a way of working smarter, not harder. And so I would encourage you to hang in there, keep working lots of examples, watch Patrick JMT's videos, get into your textbook. If you're one of my students, my textbook is not what we're using for this course. We're using NC State's text, Calculus 1 for engineers. And get in there and do the problems. All the odd problems are, most of them, have solutions attached, and not just like the answers, but how they're worked out, and some good comments in there. So the only way to get good at this is by practice, practice, practice. So until next time, have fun with Calculus 1.